start this recording and just make sure I'm not on mute. That would be the icing on the cake, wouldn't it? So as I scurried out of here, I said, oh, I posted an assignment. Oh, but it hasn't refreshed. Hopefully I did. Yeah. So assignment 2 and assignment 3. Assignment 3 is just itty bitty because it's on categorical data, which we'll start and finish today. And so just small. But I gave you a week to work on them. So they're both due January 30th. Yeah. All right. Any questions before we start? Luckily, we don't really need to do much in terms of review. Status bar. Okay, sure, I don't know. Got it. I'll just put it here. So 2.2 is categorical data, but just in terms of review, we talked about, we focused on the quartiles and the 5-number summary. And so finding the 5-number summary, which is the minimum Q1, the median Q3, and the maximum. And then we use the 1.5 IQR rule to figure out if there were any outliers. And then we use the 1.5 IQR rule to determine if there are any outliers. Right, we might have suspected outliers, but then we take the interquartile range, which is the distance between Q1 and Q3. And so the IQR is Q3 minus Q1. And then 1.5 times the interquartile range. Let's see here, where's the pointer? 1.5 times the interquartile range is what we're going to allow on either end from each quartile, right? So from Q1, we're allowed to go down 1.5 times the interquartile range before it's considered an outlier. And from Q3, we're allowed to go up 1.5 times the interquartile range, right? And so we said that the lower bound for outliers is Q1 minus 1.5 times the interquartile range, and the upper bound is Q3 plus 1.5 times the interquartile range. And I feel like we talked about some graphs, some heat maps and things, but that's the meat and potatoes from last week, or at least last day. And so now categorical data, right? Categorical data, all we have, right, in terms of our data, now we have just data that fits into categories, right? What color is your car, right? And so car color is a categorical variable. There are lots of categories, right? Broad strokes, right? We could have a black car, we could have a silver car, we could have a white car, we could have a red car, right? And so on and so forth. And so now our data set, right? We go through the room, we would have a list of just car colors, right? And there's nothing really that fancy that we can do with that data besides summarize the counts in each category, right? And so, well, should we do it? Who has a black car? Me. Only me? 1. Who has a silver car? 2. I think everyone has cool color cars. How about a white car? 4, 5. Doesn't matter. How about a red car? 1. Cool. clearly missed a bunch of colors, etc. Nice. Right. Counts in each category, that's about as fancy as we can get, right? What could we do? We could, so these would be our raw counts, right? If we just kind of only consider these car colors, that's fine. Then what could we do? We could talk about the relative percentage, right? I have how many cars here? 1, 3, 8, 9, right? And so I could talk about the relative percentage or proportion, maybe. Let's start there. Aren't those the same? Yes, they are, sort of. The relative proportion would be 1 out of 9, 2 out of 9, 5 out of 9, 1 out of 9. Right. We can convert that to a decimal and we can talk about percentages, right? So here in this example, this total is 9, unless, I don't really trust myself today, but feeling good about that addition, I guess. What do you want to make sure? These proportions or fractions, they have to add to 1, right? You've got a common denominator, so that's fine. Okay. But one thing that we're going to notice today, or really, really emphasize today, is that a proportion is a probability, which is roughly a percentage. I say roughly because I'm picky like that, but also because we have to multiply by 100, right? A percentage is a proportion times 100%, right? So if the proportion is 0.3, right, then your brain probably just kind of automatically goes 30%, right? And so here, if we say the proportion is 0.3, right, then the probability, or sorry, the probability is still 0.3. Okay, fine, I'll keep it. The probability is 0.3, but the percentage is 30%, right, multiplied by 100. Huh? Way funner class. Or maybe they're just getting snow off their boots. So that's one of the things that I'm going to harp on quite a bit in the next chapter, in chapter 3, when we focus on probability, right, which we're going to start today. So that's why I want to get it up front and center. But all these 3 P's are interchangeable, right? I could ask you for a percentage, I could ask you for a proportion, I could ask you for a probability. The way you find those things are all the same, right? If I ask for a percentage, you have to multiply the end amount by 100, but that's the only difference. Okay. So we can step it up a notch, right? Here we just had a table of counts or even relative proportions, or could convert these to probabilities, right, if we wanted to. But if we talk about 2 categorical variables, okay, which is more interesting, obviously, than just 1, okay, then I love her examples because they're always kind of edgy, but maybe just to me, I don't know. But a contingency table summarizes the relationship between 2 variables, 2 categorical variables. Okay, so 2 categorical variables, when we put them in a 2-way table like this, is called a contingency table. And so what we have in this case is we have the student's gender and whether or not they're looking for a spouse while they're in college. So yes, no situations, male, female. And so here, right, we've got a summary of all the counts. And so what can we do here? For example, there were 137 females sampled, right? And 137 out of 207, right? And maybe I'll do this. We'll call these the marginal totals. And maybe I'll put this, sorry. These are the marginal totals. Right? They're totals, they're in the margins. You don't need to memorize that terminology, but usually we put those totals or we add them in afterwards if we don't have them, right? And so, which means that we've got this 207, which I inconveniently drew over, but our total sample size, right? The number of people that we surveyed is 207. That's the overall total. And so here, right, we've got these joint totals, right, or these joint counts. And just for being able to talk about all of this table here, these are joint counts. Usually we talk more about these in terms of probabilities, right? 86 out of 207 were of people sampled were female and not looking for a spouse. Right? From this, we can make the extension later that the probability of randomly sampling a female and they're not looking for a spouse while in college, right, very specific, is 86 divided by 207, right? That's where we're going to take it. But for now, we're just looking at this table. Okay? So going back to these totals, okay, we've got the total number of females sampled regardless of whether they're looking for a spouse or not, right? The total number of males sampled regardless of whether they're looking for a spouse. But then we can flip the script and we can talk about, okay, well, how many were not looking for a spouse? 138 out of 207, right? And so we can use all these counts to answer a large number of questions. But here we're just introducing what a contingency table is and all the little parts of it. I will say, if I can find a color, well, that's boring. How about light blue? We often convert these raw counts to percentages. Convert these raw counts to percentages or proportions, right? By dividing each value by n. By dividing each value by n. And that's pretty much all we can do for categorical data, right? We stepped it up. We've already got 2 categorical variables. But what we can talk about is is there a relationship between gender and whether they're looking for a spouse? And I think we jump back to it, so I'm not gonna do it here. I honestly can't remember right now. We'll see. So this contingency table is the numerical summary. Whereas we might want to visualize a categorical variable. And so to visualize a categorical variable, we use bar plots. For us, I only want to use a bar plot, and I'll talk about pie charts just briefly. But a bar plot or a bar chart is, you've got bars representing the count in each category, right? And so we said that from this table, we had 137 females and 70 males, which we can represent visually like this, right? It's only because I have the data from the previous slide that I know this is 137, right? But we can get a pretty good idea about what the count of females is versus the count of males. Right? For that reason, it's usually better to talk in terms of the relative frequency bar plot, okay, where we convert it to a percentage or a proportion. So 137 out of 207. Where's my trusty calculator here? 137 over 207 is roughly 0.6618, blah, blah, blah. Oh boy. There. All right. 70 over 207 is roughly, well, what would it be? It should be 1 minus this, right? And so if I use this as my rounded value, then I can do 1 minus 0.6618, whoops. Roughly, oh gosh, 0.3382, right? This is 1 minus 0.6618. Or if you do 70 divided by 207, I get 0.338164, blah, 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 which would round to 0.3382. And so here we've got these relative frequencies, right, as a proportion, versus here we've got those raw counts. So it's the same setup as we had in the tables, right? We could report the raw counts, or we could convert them to proportions out of the grand total and look at them that way. Why would we likely prefer this one? These bar plots look the same, right? So that's not an issue, right? But for me, saying 66% of the sample were female, that tells me something, right? My brain doesn't do well with 137 versus 70, right? Can get a pretty good idea, but I would have to do 137 divided by 207 and kind of get there in my mind, right? Usually our brains deal better with proportions or percentages. And so, of course, these bar plots look like histograms. We're used to seeing histograms, but histograms have a numerical x-axis, right? So they're on some continuous scale, whereas, of course, here we've got these categories on the x-axis. The x-axis in a histogram is a number line, which of course means that the order of the bars can't be changed, while in a bar plot, the categories can be listed in any order, although I think I briefly mentioned it, that if you have an ordinal variable, then it probably makes more sense to list them in that order. Okay. questions so far? Yeah.
Is this data trying to show anything? Because if we're trying to see like percentage of males and females that are looking for spouses, we should be going up through 07, we should be going up the totals.
Yeah, so it depends. So this is like the most basic kind of just gender focused representation. I feel like we're gonna go and keep going and talk about, is there a relationship between gender and whether they're looking for a spouse in college? So we'll take it there. We'll get there.
Okay.
Yeah. But just starting with the basics, just introducing a bar plot, basically. You got to slow down. So here, what if we want to know, does there appear to be a relationship? Okay, I'm going to highlight that, between gender and whether the student is looking for a spouse in college. Okay. And I'm noticing there's a typo here. This isn't a percentage because it's just as a decimal of 0.37. And so just to be consistent, I'm going to call this a proportion. And this is a proportion, right? Because what can we do? We can say, okay, the proportion of females looking for a spouse, right? Yes, they're female and yes, they're looking for a spouse, is 51 out of 137, right? So now they had to be female, right? In order to be a female looking for a spouse. So they had to be female. And then how many of those females are looking for a spouse? 51 out of 137. And so then we get 0.37, or if you prefer, 37%. You can do the same thing with the males. It doesn't matter that we had a smaller group of males in our sample. That's fine because we're going to convert it to a proportion, right? And so now we're saying, okay, out of all the males, the 70 males, 18 of them said that, yes, I'm looking for a spouse. And so we get 18 out of 70 is 0.26, or 26%. Now, we want to talk about, does there appear to be a relationship here, right? Let's take it on the flip side and say, well, what would this look like if there was no relationship between gender and whether they're looking for a spouse in college? Then, if there was no relationship, we would expect these to be the same, right? Relatively the same or close enough, right? And so this is where it gets a little bit tricky. My gut says that, yeah, 26 is quite far from 37. So I would conclude that, yeah, there's probably a relationship here, right? The gender determines the probability of looking for a spouse. I think it would have been funnier if she had flipped them, but maybe that's up to me. And so here, we're going to say here, if there, and maybe I'll give myself more room. If there is no relationship, we would expect the percentages to be roughly the same, right? Regardless of gender. We would expect the percentages to be roughly the same for the two genders. And of course, there are tests that we can run to determine, yes, 37 is significantly different from 26, but for now we're just developing that kind of eyeball technique, which is usually kind of good enough, right? And so here, since, whoops, oh my gosh, since 37% and 26% are quite different from each other, right? We suspect that there is a relationship. Are quite different from each other. We suspect there is a relationship between what? Between gender and looking for a spouse. Between gender and looking for a spouse. Nice. So, without the actual test to see if these are significantly different from each other, that's as far as we can take it. We suspect there's a relationship here, right? And what's one of the things that we might get tripped up on, right? 26 and 37 are quite far from each other. That's allowed, right? But one of the things that I know trips people up is, well, what if I need it to be 50-50, right? That's not necessarily the case, right? If, let's say, on average, 30% of females are looking for a spouse and 30% of males are looking for a spouse, that's okay. Then they're relatively the same still, right? And so what would it mean for the flip side? It would mean 70% are not looking for a spouse in the females and 70% are not looking for a spouse in the males, right? And so they don't have to be evenly distributed, right? Just similar across the groups, right? Across the genders in this case. Okay. So if we have two variables, like in the contingency table, then there are a couple of visualizations that we can do. We can make a stacked bar plot, side-by-side bar plots, and standardized stacked bar plot. I'm pretty sure there's fancy examples here. This is a stacked bar plot. Let's say this is 1, 2. Here I've got 1, here I've got 2. I don't like this one. It's called a mosaic plot. I find that it's hard to read, which defeats the purpose of visualizing a variable, right? Or two variables even. So the difference is between these two. So here I've got a stacked bar plot, again with the raw counts, right? Versus the relative percentages or the relative frequencies, right? And I've split it up. So we've got the light blue for the yeses, dark blue for the no's. And then this one's easier to compare because then I can see that there's a slight difference in the genders. Now, again, I don't like mosaic plots, so I'm going to skip it. I don't like these. I can't just say I don't like them. I don't like them because, well, I guess I can. But I don't like them because they're hard to read, right? I find they're hard to read. Which defeats the purpose of visualizing data. Which defeats the purpose of visualizing data. Right, because here, pretty sure This is a famous data set, the Titanic data set, where we have information on whether someone survived or died, and then their age and a bunch of other things. And it's kind of a go-to data set for analyses, especially for categorical data. And so here we've got the number of adults. Well, the bar, the overall adult bar is quite a bit thicker because we had more adults in our data set, whereas the child bar is is very, very thin because there weren't very many children on the Titanic. So this, I'll just make a note that this is the Titanic data. If you Google it, you can find it. It's available, just easily available, and it's just kind of a fun one. Okay. I guess it's not fun. So pie charts. I don't like pie charts either. Why? Well, because they're hard to read, right? And the textbook's pretty cute. It says this is the only pie chart you'll see in this entire textbook. And it's just to basically bash pie charts. And so can you tell which order encompasses the lowest percentage of mammal species? So here we've got all these species. This would be hard to summarize in a bar plot as well, but it might be easier to read is all. Okay. And so one of my things is a pie chart, right, is really hard to read. Okay. And the only time that it's easy to read is if it's only two categories, right? And so a pie chart is only easy to read if there are two categories. If there are two categories. But if I tell you that, I don't know, 70% of Titanic passengers died, then your brain also knows how many survived, right? So you don't need to illustrate that with a pie, right? You could just summarize it with a number, right? And so here, we might have something like this, right? Died and survived. Yeah. But we could just summarize this. Oops, just summarize this with a number. For example, 70% died, right? That implies, therefore, 30% survived, right? Our brain handles that really well. And there's all kinds of interesting studies on what our brains can handle kind of naturally and what's difficult for our brains. And pie charts are one of those things where we don't do very well picking out these pies. And so I'm going to say never use a pie chart. And now you can act all hoity-toity if you see someone using a pie chart. You shouldn't do that. It's hard to read. So I understand that they're kind of fun to use at times, but the donut chart was really big at one point. The donut chart, oh man, just they cut out a hole in the middle. It's even worse, in my opinion. Okay. So all kinds of weird takes, right? But right, a bar chart is better, is always better. even small differences in the bars, right, versus a bar chart. If you have an example like this, and you've got a bar like this, and a bar, well, and a bar like this, and a bar like this. Okay, that was a bad example because I drew them like the same, right? We can tell that this one is just a little bit shorter than the other one, right? Very, very subtle differences that we can see, right, with the bars. Okay. What if we bake in some numerical data? Okay. So now, right, just to recap, right, we've talked about a numerical variable. We talked about histograms for visualizing numerical variables. And then we use the scatter plot to visualize two numerical variables. And then bar charts for a single numerical variable. And then stacked bar charts or some version of that for two categorical variables. I said that wrong, but and now we've got a numerical variable, one numerical variable, and one categorical variable. Usually what we do is what's called a side-by-side box plot. And so here, does there appear to be a relationship between class year and the number of clubs students are in? And so the number of clubs that a student is in is a numerical variable. Numerical, and class year is categorical. So what we can do is we can put the categories on the x-axis, and then we can put the numerical variable on the y-axis, and then we can make individual box plots, right? Which is something that we can use to visualize numerical data. Okay. I've somehow lost my time on here, but I think I'm okay. Okay. So then we put our numerical variable here and our categorical variable here. There are lots of things we could talk about here. We could say, okay, if I know, let's focus on the median for a second, right? Then the median is the central bar in the box. This one's kind of funny looking. Means that 25% of the data were just at that point, right, from Q1 to the median. So here, right, I've got the median here, the median here, the median here. The median seems to be about the same for each of the groups except for the juniors. Now, I never know what these things mean because I am not American, but it doesn't matter. And so here, right, higher for juniors. Okay. And that's it for categorical data. Okay. Only because I am really not feeling very well. And I might just call it. Is that okay? Sorry, guys. Otherwise, I might faint. And that wouldn't be very good. So we'll end it there. We'll start probability next day. Sorry about that, guys. Feel free to read ahead, though. Okay,